All right, today we will be addressing Charles' law. Charles' law is the relationship between volume and temperature. The equation for this is V1 over T1 equals V2 over T2. This is a direct relationship, so as one goes up, so does the other, and vice versa. Now, one really important thing to remember for this is that when you deal with temperature and gas laws, everything has to be in Kelvin. So anytime you see degrees Celsius, you have to remember to add 273 in order to get Kelvin. If you do it with Celsius, you'll get the wrong answer. So let's get started with example 1. An 850 milliliter balloon at 20 degrees Celsius is put into a refrigerator at 5 degrees Celsius. What is its new volume? First red flag I see is those degrees Celsius, so I'm going to cross out 20 degrees Celsius and change that to 293 Kelvin. So all I did was 20 plus 273 gave me 293 Kelvin. I'm going to move on over to the 5 degrees Celsius. Again, cross that out and change it to Kelvin. 5 plus 273 gives you 278 Kelvin. All right, now I can move on. Let's go through and label what we have. An 850 milliliter balloon. Milliliters is volume, so we know this will be our first volume. And 293 Kelvin is a measurement of temperature, so that will be T1. Put into the refrigerator, and it changes to 278 Kelvin. Again, that is temperature, so this will be our second temperature. Now, before I move on to the math, it's always good to do our predictions. So, what do we see here? We see the temperature goes from 293 to 278. It's going into the refrigerator, so it makes sense that the temperature is dropping. Since this is a direct relationship, we can then assume that the volume will also drop. So we should expect our balloon to get smaller when we're all done. Let's jump into the math. V1 over T1 equals V2 over T2. I like to see my equations as a checklist. So we're going to go variable by variable and see what we can fill in. V1. Do we know V1? I see right here we have V1 is 850 milliliters over T1. We know T1 is 293 equals V2. We don't have a V2 labeled, so I know that will be my variable, so I'll leave it as V2 over T2. And we have T2 is 278. Now, when we have lovely ratios like this, the easiest thing for me to do usually is to cross multiply and divide. So I'm going to start by picking the diagonals. So we have 293V times V2 equals, on the other set of diagonals, 850 times 278. All right, let's first deal with the side that doesn't have the variable. If you do 850 times 278, you should get something along the lines of 236,300. Big number. Bring down the V2 and the 293. In order to isolate the variable, we are going to do the opposite of what we already have. So right now it's being multiplied, so we need to divide by 293 on both sides. This cancels. 236,300 divided by 293 will give us 806. Now, what is our label? Remember, you look at this variable as a V, so you can go back to the problem, find our other V was labeled with milliliters, so we know that this too will be in milliliters. Quick check of our work. We said that in our prediction that the volume should go down. It started at 850, it ended at 806. We were correct, so that's a good way to check our math. All right, let's move on to example 2. Go ahead and take this time to pause, try the math yourself, and then go ahead and press play and see if we get the same answer. Example 2. A 1.2 liter balloon is inflated at 22 degrees Celsius then carried outside. If the new volume is 1.3 liters, what is the temperature outside? Now, We're doing gas laws. My red flag is my degrees Celsius, so I'm going to cross that out. I'm going to add 273, which would give us 295 Kelvin. Now we can go and label our variables. So 1.2 liters. Liters is volume, so that'll be our V1. 295 Kelvin is temperature, so that will be T1. And the new volume is 1.3 liters, so that will be our V2. What is the temperature outside? Let's do our observations and prediction. I can see that my volume is going from 1.2 to 1.3, so that is an increase, which means that we can expect at the end that our temperature will also increase. It should end up higher than the 295 it is right now. All right, let's write our equation and fill in what we know. V1 over T1 equals V2 over T2. We know that V1 is 1.2, and we know that T1 is 295. We know that V2 is 1.3, and T2 is unknown, so that will remain our variable. All right, we can do our cross multiplication here. So we have two sets. I will start with 1.2 times T2 equals 295 times 1.3. Let's start with the side that doesn't involve the variable. So 295 times 1.3 should give us 383.5. Bring down the 1.2 and the variable. Divide both sides by 1.2. And our T2 should be equal to 319.6 Kelvin. That is a very hot, hot temperature. That's actually about 115 degrees Fahrenheit. So we predicted that our temperature would go up, and it did indeed.